Okay. So yeah, by popular request, I'm going to talk about polarization. I'm wearing the shirt saying "Don't panic." I hope will reassure everybody. So this is a polarization map of our galaxy. You can see all the little vectors there. Can everybody tell me what's wrong with it? There's a really fundamental thing that's actually not wrong with the image, it's wrong with the camera, which you can't see. I'll tell you what it is they don't actually say what those vectors are. Are they E fields or B fields? And this is a common problem when people show polarization, it's quite ambiguous. Anyway, clearly there's lots of information there and we'll be returning to that. So let's start right at the beginning. So, and we'll quickly get into more interesting stuff. But for people who aren't familiar with polarization, on the left there, you've got just a little thing showing what polarized light is. When an electron gives off a photon, that photon is 100% polarized, always. It's in one polarization state. But what we normally observe are beams of light, which hold mixtures of photons. And so the polarization is all over the place. And so in optical, with optical light, often you can put in a polarizer like a pair of polarized sunglasses, and that will produce polarized light. What's important is that also scattering is a very important way of producing polarization. So at the top right there, you see unpolarized light coming in and bouncing off a non-metallic surface. Metallic surfaces don't do this, and that will give you some degree of polarization. And the final point I want to make on this slide is that when we talk about polarization, like that diagram on the left, it's only showing one plane of polarization. And we really need to define whether that's E, the electric field, or B, the magnetic field. And the bottom right, you can see that the electric field is always perpendicular to the magnetic field, but a light ray always has both of those. Right, so polarized sunglasses, what this means is that polarized sunglasses are a polarizing filter. If you look at the bottom right diagram, you can see without polarized sunglasses, you can't see the water very well. But as soon as you put your sunnies on, you can see right through the water. And that's because that scattered light is polarized, and so that at a particular angle, and so the sunnies will block that out. The polarized sunglasses is actually made with the direction of polarization already arranged, so you can see through flat horizontal surfaces. Another thing of polarization is that the blue light in the sky is scattered, Rayleigh scattering, and so that is also quite high polarized. So if you put on your polarized sunnies, and as you move around, you'll find different parts of the sky get darker or lighter. If you twist your polarized sunglasses, you can actually see the direction of the sun, which is said to have been used by Vikings to navigate. Anyway, right, getting on to radio astronomy. Oh, by the way, please do just shout out if you have any questions. I think it's meant to be a tutorial, so let's try and make it interactive rather than just me talking. So anything so far, questions or comments? Right, so this shows the black line here is an electron, normal synchrotron radiation whizzing around in a magnetic field. And as it whizzes round, we know it gives off radiation because it's being accelerated. And the polarization of that radiation is seen from the observer. It's going like this, and it's creating effectively electric currents. So the E field is vertical in this picture, and therefore the magnetic field is horizontal. So the magnetic field of the polarization from that synchrotron emission is parallel to the magnetic field that's causing it, which is very handy. We also get circular polarization, and in circular polarization,
I've got a question, Ray.
Yeah.
Just on your last slide, you said it hits the magnetic field and it starts spiraling and then accelerates. How? What speed does it? What's its maximum acceleration?
So when I say accelerate, I'm using it in the sense that it's not going in a straight line, it's going in a circle. So from a point of view of physics, you say it's accelerating as it goes round that helix, which is in a circle. That's all I meant by that. But it's the fact that it's been bent round, which is what makes it radiate the synchrotron emission. Okay, in circular polarization, it's very similar, except that now the plane of polarization is rotating every wavelength. And so the E field might start at the top. It goes over 90 degrees after a quarter of a wavelength, and our half wavelength is pointed down. After one wavelength, it comes right back up. So in circular polarization, the polarization is going through a helix, but that helix is exactly one pitch of one wavelength. Okay, so what about antennas? The simplest linearly polarized antenna is the TV aerial, Yagi, on the top left there. And because the elements are picking up the electric field and they're horizontal, that means the E field of that linear polarized radiation is horizontal, which means B field is obviously vertical. Now, in things like the compact array, we also use linear polarization. Our feeds, I was going to say, how many people, I can't see pictures of people, that's annoying. I was going to say, hands up, who, give us a yell. How many people have been inside the vertex box on the compact array shown on the right there? Yell out.
Yes.
Yep.
Yep.
Yeah.
Yes.
Yes.
Okay. So,
No one lets me anywhere near the telescopes.
oh, you've got to go up there, get a chance. It's really cool, actually. So you see the dishes down.
Sorry, Ray.
Yeah.
Is it really cool because they're cryogenically cooled, or?
If
Sorry.
it's cool in there because of the cryogenics, then we've got a serious leak, and that'd be a real problem. No, it's cool because of the air conditioning, actually. Right, on the antennas in the lower right, you can see that little, actually you can hardly see it. There's a little bump sticking out there. And that's the vertex room. If you go inside there, this is what you see. And you see these big horns here. And those are the horns which are picking up the signal. And you see one horn at the top and middle there. And can anybody say what that receiver in the middle at the bottom is?
Multi-beam.
Yeah, it's the multi-beam feeding off parts. So all our receivers have got these characteristic horns, but the way we couple, so those horns will pick up any polarization because it's circular, but the way we pick up the radiation from them is two little quarter wave probes sticking into the feed at the bottom. I couldn't find a really good picture of it, but you have to take my word for it. There's just a little metal spike sticking. You can actually see the coax connectors on that middle top diagram there. Those little coax connectors are just connected to a metal spike sticking into the horn, plus some dielectric funny stuff as well. So with the compact array, we use linear polarization. Another feature of this turret here is one thing we decided in the design of the compact array is that we wanted to have our receivers on axis rather than spread around, which you'll see in a minute in the VLA, because we were very keen to get the polarization right. And it's really hard to get polarization right if your feeds are off axis. So that's why we've got this little carousel. So when you're observing at L band, you've got that bloody great white feed in the center. Those other feeds you see are for the higher frequencies. And if you change band during the observation, that carousel is flipping backwards and forwards during the observation. Okay, circularly polarized antennas. If you want to make something like a Yagi, you can make a helix like that. And that gives you a circularly polarized signal. That's actually really good, actually used in communications quite often if you're not sure what the polarization of the incoming signal is. So for aircraft and so on, where the angle might be a bit funny. And the VLA shown in the center also uses circular polarization, I think for historical reasons. And that shows the corresponding focus cabin in the VLA. And you see in their case, they don't have a carousel. All the feeds are mounted at slightly different positions near the center of the dish, and then they tilt the subreflector to point at the different feeds. One consequence of that is that the polarization of the VLA is an absolute bugger to calibrate. And doing polarizer, you guys use the compact array, you're so used to just observing, and you go through GPCal and things, and all polarization sorted out, and you just produce an IQ and UMAP. With the VOA, people will produce an IMAP, Stokes IMAP. So I haven't talked about Stokes yet. People produce a total intensity map, but to do polarization, you've got to be a black belter with the VLA. Less so now, but something used to be the case. And so that's why we decided with the compact array that we wanted to put our feeds down the middle. The reason we chose to use, yeah.
Was there any discussion on changing that for when, for when they expand to their version of the SKA? Or if they end up going that way?
I remember at the radio school, Rick Purley talked about it, that the VLA P-band receivers, which are just a dipole lashed to the subreflector, were very controversial for being dipoles. And that some of the newer VLA receivers are actually linear, and they've got quarter wave plates in them to turn them into circular, because American scientists wanted circular correlations. And ALMA was a big crap show as well, because Americans wanted circular, and everyone else who knew how to do this stuff said, no, linear is the way to go.
Yeah, absolutely.
But I also remember reading that the most telescopes receivers are all left or right circular, and it's just half a dozen turns of wire around a plastic flower pot.
Yeah, basically they use a helix like on the left hand.
Yeah, but literally around a plastic flower pot as a format.
Yeah.
So they're not that hard to make.
So if you have circular, can you derive linear or not?
Yes, you can.
Okay.
I'll get onto that in a second. So the other thing, doing polarization with the VLA is really hard, but it's become easier because you can basically get better at engineering and so on. And so with the compact array, we said, well, measuring linear polarization is pretty straightforward now. One of the reasons the VLA uses circular, because if you want to measure linear polarization, it's best to measure it by combining the outputs of two circulars, just the way the errors work. If you want to measure circular, you want to combine the outputs of two linears, but nobody ever cares about circular. So the VLA said, oh, we're going to put circular feeds on so we measure linear really well. With the compact array, we said, well, we pretty well know how to do linear. We reckon we can do it pretty well even with the linear feeds. But if we put linear feeds and put them in the center, then we can measure circular polarization, which is essentially impossible to do with the compact array. It's very hard to calibrate. And we'll be exploring a new part of parameter space. More about that in a minute. And I've written right-hand circular, left-hand circular. Oh God, I'm running out of time already. Let's skip that. You can ask me about that later. Oh, why is it doing that? There we go. Okay, so now I'm going to have to introduce the dreaded Stokes parameters, IQ, U, and V. And for basic engineering reasons, it's convenient to think of polarization in terms of these four parameters. So is that the first one? Yes, it is. We say that if you've got a polarized wave come towards you, if you measure the total energy in the wave, regardless of polarization, that's what we call I, the total intensity. And then we divide up the way the vector is by, as in these diagrams in the top left there. So if it's in the x-axis, the plane of polarization, we say that's a Q signal. If it's in the y, we say it's a minus Q signal. If it's at 45 degrees, we say it's U, and it's plus minus U, depending on the angle. And then V is circular, and you've got circularly polarized. And so you can invert that. And so Q and U tell you about all the characteristics of the incoming signal. They're a good way of doing it because you can combine them for things that aren't 100% polarized. So things which are a mixture of polarizations can be well described by the Stokes parameters. If you want to measure the total amount of linear polarization, that's the square root of p squared plus u squared, and the total secular polarization is v. The way we actually do it in practice with the compact array is, okay, we've got these linear feeds. On one of those feeds, we have an X and a Y, just two little quarter wave probes like that. And we take the X and Y signals from each feed. So when we cross-correlate the signals from two antennas, at the top, we've taken the X from each of them, and we call that XX. The next one, we've got the two Ys, we call it YY. And then we've got XY, where we've taken X and multiplied by Y, and also Y, where we multiply by X in the other order. Okay, and if you want to turn those in Stokes, you've got the conversions on the right. So total intensity, you just take the top two signals and add them together, and so on. You see it there.
Sorry, so we can't do like polarization with single dish?
Oh, sorry. Yeah, so single dish, you can do the same thing. You can actually have two probes. I'm talking about interferometers because it's what most of us mainly use. But yes, sorry, in the single dish case, you do exactly the same, but all on, so you can't take cross correlation between the, so if you have an X and a Y feed on a single dish, the total power is just the sum of the power in those two. But the cross terms, the X times the Y, then you see the Q and the U and the V, same as here. Oh, and the other thing, Pete, you asked about circular feeds. They'd have a very similar diagram on the VLA, and they'd have left hand and right hand, and they'd have RR and LL, RL and LR, and very similar. So I is RR plus LL, and I'm not sure about the others. They might be.
So they have a left hand and a right hand receiver.
That's right. Yep. That's
V
right.
is the difference of the parallel hands for circular, and Q and U are
That's right, yeah. So it's RR minus LL for V. Yep.
And Ray, very 15 seconds practical tip in Myriad when you're doing a data reduction outcap. For example, instead of I, Q, U, and V, you can select XX.
Yes, you can.
Stokes and
That's right.
YY, which sometimes can really, really help a lot.
Okay. Okay. So how do we interpret this? The total polarized intensity formally is the sum of squares of Q, U, and V. Because V, in practice, most astrophysical sources have very small amounts of circular polarization. People just approximate those Q squared plus U squared. And so it's sometimes called L for linearly polarized intensity. People often approximate it as P. And often we use the third bullet point. We talk about the percentage of polarized intensities. That's Q squared plus U squared, square root over I. And then if you want to measure the position angle, that's the arctan of U of Q. So here we have an image on the right, and you can see the caption at the top says B of polarization. And so that's correctly labeled. He's telling us those are the B vectors derived from IQ, U, and V. And you can see that spiral galaxy has got a magnetic field basically swirling around and coming out at the ends. So in this case, they've used, so that's probably VLA, I guess, to measure the polarization, and they've got a nice polarized map. And what they've done, they've shown they've used the lengths of the lines to indicate the percentage of polarization. So if you look right at the center, you'll see the lines are really short. So that's a low percentage of polarization. And on the far left, you can see a really long line. So that emission there is probably many tens of percent polarized. I'll show you an example later of an image where they don't say whether it's B or E. It's a very common problem. A lot, you get papers published showing these vectors and they don't say whether they're showing the B or the E vector, which is, I think, unforgivable. Anyway, I'll try not to rant. Okay, circular polarization. So in things like pulsars and radio stars and masers, you get really high circular polarization. So I realize I'm showing my bias by saying it's unusual, because I'm sure if she is there, you'll say no, most of these things are polarized. But if you're working on extragalactic continuum sources, there's very small circular polarization. It can get to the highest anybody ever sees, about 0.5%. And that's when you've got the jet of the blazar pointing right at you. And if you remember, the electrons are going around a magnetic field line, so they work a bit like a helical antenna and can generate circularly polarized radiation. In fact, that's thought not to be the main source of circular polarization. It's more to do with the fact that you start off with all sorts of polarizations, but the material that's going through as it goes down the jet tends to sort out the, separate out the horizontal and vertical, and introduces a phase shift, which then gives you the circularly polarized jet. The interesting thing is that if you've got a jet which is made of electrons and protons, the electrons are whizzing around, protons are going really slowly, so it's fairly easy to get a net circular polarization. But if the jet is electrons and positrons, and everything the electrons are doing, the positrons do the same in the opposite direction. We don't know whether jets from AGNs are electron-proton plasma or electron-positron plasma. So if you can measure the circular polarization, which is really hard to measure, then you can tell what the jets are made of. So as I say, we designed the compact array to be able to measure it really well, and that worked out very well. My PhD student, Dave Rayner, published the paper in 2000. He spent his entire PhD trying to fix the various errors of the compact array, but eventually we got it right. We're measuring the standard deviation or standard error on the polarization was about 0.01%, or 10 to the -4.
A quick question. Did you come ever across a catalog of circularly polarized sources? For example, you know, in the future EMU survey, can we have a catalog of these sources? Is that something that it's possible? Do you know if it exists?
Sorry, I don't. What do you mean? What do you mean?
A catalog of polarized, the circularly polarized sources, like we have a catalog of all point sources in the field. Did anyone ever done anything like that?
I've never seen anything like that. All we ever see is a single circularly polarized source at the nucleus.
Yeah, but you know, we're going to have a big, huge EMU field. We're going to have hopefully a lot of these. Why not have a catalog of those?
Yeah. Why do you think you might see a couple?
Well, that's the best way to search for these sources. You know, to match them. If you're going to have a whole sky field full of these sources, then you can start doing a science with them.
Is this more possum's remit than emus?
I'm sorry?
Isn't this more possum's remit than emus?
It is actually, yeah. So possum is.
But there is no catalog at the moment of any circularly polarized sources in the field. No,
that's right. And of course, ASCAP isn't compact array. We're not going to be able to measure circular polarization that well with ASCAP. I'll tell you, we're almost out of time, but I'll tell you one anecdote from Dave Rayner's PhD. We had this funny effect where we'd measured all the leakage terms so carefully, and yet we'd suddenly get an error which flipped as sources went past transit. So we'd be observing the source with everything perfectly calibrated, and as it got up to transit, suddenly there'd be a glitch in the polarization, and that would continue stable for the other half. And we spent ages drawing diagrams, analyzing data, before we found it's at transit. Of course, finding it's at transit was a long way down the path. And in the end, we got Mike Kesterman to go up and stand up there in the focus cab and see if he could see anything that changed at transit. And sure enough, as the telescope, so he's standing there while the telescope was pointing and moving. And as it went through transit, he heard a clunk. And when we looked very carefully, we found that this feed rotator was held in place by a pin. It's actually a thing like this with a U-shaped groove. And the U-shaped groove goes into a thing to hold the rotator in the right place. And there's just a bit of play in this groove. And we realized in the design of the telescope, a U-shaped groove is exactly wrong because you're going through the cos theta part of it. It's not what you really want is a V-shaped groove. So we got the telescope engineers to change all these things from U-shaped grooves to V-shaped grooves, and that fixed our last leakage term in Stokes V. And it is pretty amazing that you're going from plotting these graphs as we all do, actually to get engineers to carving out a new piece of ironwork. Let's see now. Oh, talking of calibration, Luke, should I stop there or?
I think we probably should, because I'm not sure what people have next. We can just pick up next week. We'll just carry on.
Yeah, I'm exactly halfway through, actually.
Wonderful.
Any questions on any of that?
But we still have leakage in LADCA, right?
Yep, and that's actually a couple of slides further on about how we calibrate the leakages.
Hey, this is fantastic. Really, thank you.
Really good.
Oh, good. Okay, good. I wasn't sure whether it's the right stuff. No,
I'm learning loads. Yeah, excellent. So we'll catch this up again next week. Pete is going to post the video of this somewhere.
Yes.
Email it around. It might be a good idea to have another watch before next week, so you're right on board with it. So thanks very much, Ray. I think we're all done. We'll see you next week for more of that. Thanks, everyone.
See you guys.
Thank you.
Thank you. That was great.